Hello everyone, this is Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. We will go over the few concepts revised in the past couple of weeks, and then we will do as the previous assignment and then some problem questions. So this is the concepts that we were revising from the beginning of this course. Cm naught, Cm, that is the pitching moment coefficient, has a constant term and a slope. The slope dCm by d alpha is what contributes towards stability, is an indication of stability. If the dCm by d alpha is less than 0, so if it's a negative value, it's statically longitudinally stable. And we need to ensure Cm not to be positive to trim at a positive angle of attack. Neutral point is defined as the location at which the CG, it's the CG location at which Cm alpha is 0. So dCm by d alpha or dCm by dCl. Okay, so both of them, dCm by d alpha is equal to 0 or dCm by dCl equal to 0. That is the location of a neutral point, stick fixed neutral point. And the equation is given as this. Static margin is an indication of stability, which is represented by the negative slope of dCm by dCl, which gives you the distance between the CG and the neutral point. Further the CG is from the neutral point, more stable the aircraft is, but more difficult it is to control, more difficult it is to maneuver. What is control? Control is something that we introduced to ensure trimming at different velocities. So if you were trimming at this here, so this is Cm, this is Cl. The point where Cm is 0 is called trim. So that is this point, and this is known as Cl trim. So if we want to trim at a different Cl, that is at a different speed, we need to introduce something known as a control, which translates the graph to a different Cl. Higher Cl means lower velocity. So if we want to reduce the velocity at which we want to trim the aircraft, we translate the graph further. So this is what it says. It moves the Cm versus Cl graph. It doesn't rotate it. So the intercept changes, but the slope remains. This Cm naught remains, changes, but this part, the stability part remains. So the control has no effect on stability. Now the elevator is the control surface for longitudinal control. So the elevator deflection to trim the aircraft at given CL trim is given by this equation, which, as we've discussed in all the classes before, has a negative slope. So why it has a negative slope? This d delta E by dCl trim is this value. Now this XNP minus XCG for a stable aircraft is positive. Cm delta E for any conventional aircraft is negative. So the entire term, the entire slope is negative. Now coming to this term, Cm naught, we have ensured it to be positive to trim at a positive angle of attack. So Cm naught is positive. Cm delta E again is negative. So this entire term becomes positive. So it has a positive intercept delta E naught and a negative slope. So this is delta E and this is CL trim. Okay, so this is the graph. Next, we moved on to the hinge moment. So what if we were to leave the elevator? If we didn't hold the elevator at the desired location, there would be a moment. The moment and the hinge. So your control surface, this is your tail, horizontal tail. And your control surface, that is the elevator, is here. And it moves about a point known as hinge. And deflecting the elevator and change in angle of attack generate a moment about this point. So if your initial angle of attack was, if your initial velocity was at this direction, it would see the angle of attack at tail would be 0, right? So now if your next velocity were to come at this direction, you have some angle of attack, right? So angle of attack at tail would be greater than 0. And when this angle of attack increases, there is a lift generated at the center of pressure of your elevator. This lift generated produces a moment about your hinge point. This is center of pressure and this is the hinge point. So for a positive angle of attack, you have a nose down moment. So for positive alpha t, you have negative hinge moment. Negative means nose down. Similarly, if you were to deflect the elevator down, deflecting the elevator down by convention is positive. So if you were to deflect the elevator down, that is positive delta E. Again, what happens? You have a positively cambered airfoil. Effectively, it produces a lift even at 0 angle of attack. You have a lift, and this again produces a pitch down, that is negative moment at the hinge. This is acting at center of pressure, and this is your hinge. It produces a negative nose down moment at the hinge. So positive delta E gives you a negative hinge moment. Okay. So what this implies is that both the quantities in this equation is our linear approximation of hinge moment coefficient. CH is hinge moment coefficient. CH naught is the intercept. CH alpha T, CH delta E, CH delta T are derivatives. So what these two conditions indicate is that CH alpha tail is less than 0. Why? Because for a positive angle of attack at the tail, you have a negative hinge moment. And similarly, for a positive deflection of elevator, CH delta E, for a positive delta E deflection, you have a negative hinge moment. So again, CH delta E is 0. Similarly, CH delta T is also less than 0. How? Are you able to hear me? Can someone confirm if you're able to hear me?
Yes, ma'am.
Okay, thank you. So now we have another surface on the horizontal tail known as a trim tab. What does the trim tab do? So if your elevator is deflected such, right? So trim tab is something that is at the end. So if your elevator was deflected and freely floating at some angle, there would be a trim tab at the end, which again would deflect down. Okay. This is at the free condition, that is stick free, where you're not holding the stick fixed, right? So stick free condition, if your elevator is floating up, that is for an oncoming velocity, it's floating up, your trim tab would float down, would deflect down. So that means it is a positive delta T. Delta T is the trim tab deflection, positive delta T. This again produces a lift at the center of pressure of your trim tab. And this produces again a nose down moment at the hinge. This is center of pressure of trim tab. Okay. So it produces a nose down moment at the hinge. So what we see is for a positive delta T, again we get a negative hinge moment. So CH delta T is also less than 0. So these three slopes, these three derivatives are all less than 0. Now, what do we mean by float? Float is when there is no hinge moment. So when this elevator is allowed to float freely, it stops at a location when the hinge moment is 0. Okay. So putting the hinge moment coefficient as 0 and neglecting for the time being CH naught and the effect of trim tab, what we get is this value. Now we saw that CH alpha T, CH delta E are both negative. So these both are negative and has a negative sign. So what it means is for a positive alpha T, okay, so if the aircraft, if the tail sees a positive angle of attack, the delta E would float up. So it would be negative. For positive alpha T, you would have negative delta E float. Okay, so for a positive angle of attack at the tail, the elevator would be deflected upwards. Elevator would float upwards. Okay. Okay. So now for the no float condition, like where the delta E float is 0. So what it means is the required and the float are the same value. So for the delta E float, if you require the elevator to not deflect at all, that is delta E float 0, these are achieved. This is achieved how? CH alpha T, this term has to be 0. Then only you will get delta E float as 0, because alpha T, it changes, right? So CH alpha T, if it is 0, then you get 0 delta E float. How do you achieve CH alpha T 0? We saw that there is a hinge moment due to alpha T because the center of pressure, the lift produced at the center of pressure produces a negative moment at the hinge. Now, if your center of pressure and hinge are at the same point, it would produce no moment. Then your CH alpha T would be 0. So that is one way. Another thing is called horn balance. This is as explained in the video. So if this is your entire horizontal tail surface, you take the elevator, that is this part, this entire part is deflectable. The entire part is considered elevator. So when you deflect the elevator down, this portion produces the negative moment as we saw here. Now the front portion, that is the leading edge portion of your elevator, would produce a restoring moment. So the moment produced by this portion and this portion would cancel the moment produced by this portion. That is what is known as horn balance. Okay, so these are the two methods by which we can ensure CH alpha T 0, which in turn ensures that your floating elevator angle is 0. Okay, so this is the point that we discussed, all three derivatives less than 0. Okay. Next, we discuss some stick conventions. Stick conventions, as in, if we were to push the stick forward, pushing the stick forward would imply that you get more velocity. More velocity means less CL. How do you ensure less CL? You need to reduce the angle of attack at the tail. How do you reduce the angle of attack at the tail? You deflect your elevator down. So what happens? So you deflect your elevator down. It produces a lift here, which produces a nose down moment. Okay, let me just draw that properly. So this is your horizontal tail. You deflect your elevator down. To deflect your elevator down, it produces a lift here. It produces a nose down moment at the CG, which in turn reduces the angle of attack. Okay, how do you reduce angle of attack? You deflect your elevator down, positive deflection of elevator. Okay. Now stick force. Stick force is calculated how? Stick force is the force required to. Am I audible? It keeps telling me that my audio. Okay. Okay. So stick force. Stick force is the force applied by the pilot to maintain the elevator deflection. Okay. Before we proceed into this, it is important to know that the delta E required is only governed by the stick fixed static margin. This delta E required. Where is delta E? So this delta E trim, delta E required is governed only by the stick fixed static margin. Okay. So it is DCL, DCM upon DCL fixed. So delta E required is governed by the stick fixed static margin. Now we encounter three conditions. If your elevator is floating at the naturally required delta E, then the pilot need not apply any force. So that condition is known as neutrally stable. So if your elevator is naturally floating at the required elevator deflection, the pilot need not deflect it any further. So that is Fs0. Fs is stick force. Pilot need not apply any force. Now, if your delta E float is less than the required delta E, that is, if suppose your delta E float is some 3 degrees and your delta E required is 5 degrees, the pilot needs to deflect the elevator upwards by 2 degrees. So he needs to, if you have to deflect the elevator up, the elevator down is push, elevator up is pull. So you pull the stick, that is elevator up, and this condition is known as stick free stable. Now, okay, this is wrong. If it's delta E float is greater, delta E float is greater than delta E required, then he needs to reduce the elevator. So if this is 5 and this is 3, the delta E float is more than the required elevator deflection, and he needs to deflect it down. He needs to get a negative delta E. He needs to get a positive delta E, but he needs to deflect it down, right? So here he needs to push the elevator. So Fs is greater than 0, elevator down, and this condition is known as stick free unstable. Now your stick force is given by this equation. Hm is hinge moment, delta E, the elevator deflection, Ls and delta S, okay? So the stick force equation is also given by this. Once you expand and simplify the equations, you get this final equation, which will be used in some of the numericals. I've just noted it down here. What this says is that this is the term that is dependent on speed. You can see that V appears only in the first term. The second term has no V term. So this depends on speed, and this is the contribution of the stability, right? This first term is given to you by different speeds. The second term is given to you by the different stability conditions of the aircraft, okay? So now, what is the difference between stick free and stick fixed case? The only difference comes, as far as equations are concerned, only difference comes from the CL tail, okay? So CL tail is given by this equation, linear approximation, CL alpha tail into alpha tail plus CL delta E into delta E. For the hands off case, this delta E is what? Delta E float or delta E free, whatever. So when the stick is left, the elevator floats freely and it rests at a point where the hinge moment is 0. That is this delta E float. So substitute that value into this equation and you get this. Finally, we see that CLT is CL alpha tail dash into alpha tail. CL alpha tail dash is the corrected alpha tail because of the stick free condition. Okay, if you leave the stick, the CL alpha tail becomes CL alpha tail prime. That is what changes your CL tail. Now, when we use this new value of the CL at the tail in the equations, we get a value for stick free neutral point. This prime indicates stick free, Stick-free neutral point is given by this equation. Similarly, the stick-free DCM upon DCL, the negative of static margin, is given by this equation. Now what we can see here is this DCM by DCL fixed for a stable aircraft is negative. Now what about this term? CH alpha tail is negative, CH delta E is negative, tau is positive, this entire thing is less than 1 but greater than 0. CL alpha tail is positive, CL alpha wing is positive. These two are again positive. So the entire term is positive, this entire thing. So we know that for stability, we need DCM upon DCL to be negative. Any term that contributes towards a positive value is destabilizing. So what we can see is that the stick-free stability is less than the stick-fixed stability because of this, positive term, okay? So now these are just comparisons between the stick-fixed and stick-free case. We had discussed this previously. We'll just go over it. CM at the CG is CM naught and the slope. Similarly here, the slope is stick-free condition. Even the CM naught would vary, which is shown in the next row. CM naught for the stick-fixed case is the well-known equation that we've been using throughout. Here, the only difference is the CL alpha tail. So CL alpha tail, you can see, is replaced by CL alpha tail prime. Okay, CL alpha tail prime was what? This value. This value is CL alpha tail prime. Similarly, for DCM upon DCL, again, the only change is in the CL alpha tail. Okay, it has a prime here. That is a stick-free CL alpha tail. Then your X bar NP, again, the only difference is CL alpha tail. Okay. So now we move to the questions of assignment 6. This was the first question. For an aircraft, the tail area is 1/4 of the wing area, and the distance between the two aerodynamic centers is equal to 1/4 of the wingspan, and the wing and tail are rectangular in shape. In addition, they have given the following data: the weight of the aircraft, cruise velocity, CL alpha tail, tail efficiency factor, and all of the other parameters. Okay. The first question is the pitching moment coefficient at 0° angle of attack. What is the term? Pitching moment coefficient at 0° angle of attack. What is it called? Pitching moment coefficient at 0° angle of attack. What is it called? What is the term? What is it given by? Am I audible? CM naught, exactly. Okay, so CM naught. How? CM naught, we have contributions from the tail, from the wing, and the fuselage. Now, in this question, they've asked you to neglect the effect of the fuselage. So CM naught would be CM naught wing plus CM naught tail. Okay. What is the equation for CM naught wing and CM naught tail? CM naught wing is given by CM naught wing is given by this equation. Do we have everything in that equation? CMACW is given to you, okay. So that's minus 0.009 plus CL naught. CL naught is not given to you. How do you find out CL naught? They've given you the slope. So CL versus alpha. They've given you the slope of this graph, and they've given you alpha at L equal to 0, which is minus 2 degrees. So how do you find this is CL naught? How do you find CL naught? How do you find CL naught? CL naught is equal to, you have this value. How do you find this value? And you have the slope. So it's just CL alpha wing into the slope, into this magnitude of this distance, right? This angle. That's 2 degrees. Since CL alpha wing is given in per degrees, you don't have to change it. CL alpha wing is 0.09 into 2 degrees, which is 0.18. Okay. So this is 0.18, and X bar CG minus X bar AC, is it given? Yes, it's given. It's 0.031. What is this value? Can you calculate and tell me? Okay, so it is 0.00342. Okay. Next, we go to the contribution towards CM naught by the tail. Here we don't know VH. How do you calculate VH? VH is this formula, right? So what do we have here? Do we have ST? We have ST upon S. So they've said that the tail area is 1/4 of the wing area. So ST upon S is 1/4. Then distance between the two aerodynamic centers is equal to 1/4 of the wingspan. So LT is 1/4 into B, and C bar, you have C bar. So this is B is, how much is B? 10.5. 10.5 by 4 into 4 into C bar is 1.2. This value is, how much is VH? 0.5468. Okay. Similarly, we don't have E naught, so you have to calculate E naught from this. This 2 into CL naught. CL naught is 0.18 by pi. E is 1. Aspect ratio for a rectangular wing is, aspect ratio is B square upon S. For a rectangular wing, S is B into C. So it's B square by B into C, which is B by C. So you have B into C. And now this equation, like I told you initially, is valid only if your CL naught is in per radian. So we need to multiply by 57.3. How much is this value? Epsilon naught 0.75. Okay. So now you substitute all these values here. So you get VH is 0.5468. Tail efficiency factor is 0.9. CL alpha tail is 0.059 into I wing is, that is the wing setting angle, is 1.3 plus epsilon naught is 0.75 minus tail setting angle is minus 1.3. So it's plus 1.3. How much is this value? Can you calculate? Can someone calculate and tell me this value? Can someone just calculate and tell me the value? Okay. I am audible, right? You can calculate. It's a simple calculation. What is the value? Thank you. 0.09617. Okay. So now your overall CM naught, CM naught is CM naught of wing plus CM naught of tail, and that is, comes out to be 0.092926. This is the value. So this is the answer. Your next question is pitch stability derivative, Cm delta E. Cm delta E, we have a very simple equation. Cm delta E is minus eta VH CL alpha tail tau. Tau is the control surface effectiveness parameter. Now we have eta tail, which is given to you by 0.89. VH we calculated in the previous step. How much was it? 0.5468. 0.5468. 1 second. Okay, CL alpha tail is 0.059 and tau is 0.4. There's a minus sign here. Don't forget that Cm delta E is a negative quantity. So the value is 0.6581. That is this one. Cm delta E is a negative quantity, okay? So positive deflection of delta E, positive deflection of elevator produces a negative moment, okay? Trim lift coefficient of the aircraft at sea level. So CL trim, they've asked you to find out CL trim. This is very simple. What is the equation that we've been using throughout? So they've asked you to find CL trim. They've given you V trim, that is, in this case, trim would be cruise. So we use this equation and find out CL. So CL trim would be 2L. L in case of trim, lift equals to weight. So you will have 2W by rho V trim square S. 2 into 850 into 9.81 by rho is sea level, so 1.225. V trim is 45. S for a rectangular rectangular tail, rectangular wing is square by S, which turns out to be B by C. So B is how much? 10.5 into C is given as 1.2. This value is, you've solved this assignment, you have the values with you. How much is it? It's 0.5335. Okay, so this is the value. Moving on to the next question. This question I had discussed in the previous tutorial as well. I have not given the answer, but we have discussed this similar question. The hinge moment characteristics of the horizontal tail of an airplane are given to you. So they've given you the derivatives, CH alpha tail, CH delta E, CH delta T. You can see that they're all negative quantities like we had discussed. This is negative, this is negative, this is negative. They've asked you to find delta E free. Delta E free means CH equal to 0 for alpha tail and a delta deflection of trim tab. So what is the equation, the linearized equation, assuming CH not to be 0? This is your equation. And for trim condition, for the free, delta E free condition, this is 0. Okay. And they've asked you to find what? Delta E free. Delta E free is minus CH alpha tail into alpha tail minus CH delta tail into delta tail by CH delta E. Now CH alpha tail is 0.003, alpha tail is 5 plus 0.004 into delta tail is 4 divided by minus 0.0049. So what is this quantity minus? Let's do it fast. Comes to minus 6.33. Okay, every value is given in per degree, so we don't require any conversion. Minus 6.3. Okay. Next question. The hinge moment coefficient depends upon. What does it depend upon? We just discussed hinge moment coefficient. CH depends upon what? Just the tail angle, just the wing angle, lift to drag ratio, or the first option? Hinge moment coefficient. Come on. A, correct. Okay, so it depends upon tail, angle of attack, elevated deflection, etc. So this is that. Fx, statistic force can be written as Fs into G. Fx is equal to G into hinge moment. Okay, so G is given by what? So we know the formula for Fs as this. Now HM is hinge moment. This is G, right? So is equal to G into hinge moment. So this quantity is G, delta E upon Ls into delta S, this one. Okay. Next question, stick force is a function of, we had again discussed this, stick force Fs, it's the same formula, is a function of hinge moment, Hm. Okay, hinge moment. This is a question, I've just pulled it up next. This is not part of your assignment, it's the next question. For an airplane with wing loading given as above, flying at some altitude, the following data was recorded. So they've given you 3 values of velocity. And okay, this is a mistake. This is at xcg 0.02. This is the Fs in Newton. Okay, this is also Fs in Newton. Okay, find the stick free neutral point. How do we do this? So they've given, you need to solve this graphically. This was the last topic covered by sir in the week 7. So they've given you 3 values of velocity and they've measured the stick force at those three velocities for different CG locations. That is 0.2 and 0.25. So to begin with, what is stick-free neutral point? How is it defined? Your NP prime. How is it defined? How do you define NP? Someone tell me, how do you define NP? Like neutral point, stick-free neutral point. How do you define neutral point? Stick-free neutral point is defined as? Come on, somebody tell me. Okay, I'm not going to tell that. You need to figure it out. Stick-fixed neutral point, stick-free neutral point, stick-fixed maneuvering point, and stick-free maneuvering point. How are they defined? Find it out and we'll discuss it in the next class, okay? You should have known this by now. So we'll proceed with this question. What we do is, so we make a table. We find out Q values, okay? Q is what? Dynamic pressure. So we'll just make another table here. So you have velocity, find out Q, and you have Fs1. Next term would be Fs1 by Q. Next term would be Fs2. Then Fs2 by Q. And you need Cl, okay? And each of those have three values. Okay, so what is the first velocity? 50. Q is what? Q is half rho v square. Okay, so what is the first value? Q. What is Q? Just substitute the velocity value into this equation. Rho is given as 0.8. What is Q? What is the value of Q? Somebody tell me, what is the value of Q? Half rho v square. What is Q? First Q. Am I audible? Am I audible? Can someone confirm? 1000. Thank you. So this is 1000. 1000. Fs1 is given as 2 pull. Pull is negative, so you have -2. Fs1 by Q would be, just divide these two, you have, okay, Fs2 is given as 1 pull, that is again -1, okay, so you have 0.001. Cl, what is Cl? Is 2W by S 1 by rho v square, okay. W by S is given to you as 400 Newton per meter square. Rho is 0.8, V is 50. In this case, it's 50. How much is the first CL value? Just calculate this. 2 into 400 divided by 0.8 divided by 50 square is 0.4. 0.4, yes. 0.4. Now fill the table up for the other values. 57.3. What is the value of Q? One three 1.316. Okay. 131.6. And what about CL? What about CL? CL is 2W by S by rho V square. And V here is 57.3. CL is? .3046. Okay. Now next, third entry. So here it is 70.71. What is the value of Q? Here I've put 0, you understood why, right? So Fs stick force is 0. So Fs by Q will also be 0. So what is the Q for the third velocity? Q is half rho V square. So we'll take it as 2000. This is 4 push, so it is positive. 4 by 2000, 0.002. This is 2 push, so again it's positive. So this would be 0.01. And CL, 2W by S by rho V square. CL is 0.2. So what we need to do now is to plot, right? So is to plot this Fs by Q1, Fs by Q versus CL, and Fs2 by Q versus CL. So we make a graph. Just erase this part of the screen. You remember the last topic that Sir took, right? Experimentally, how do we determine the neutral point, stick fixed, stick free, maneuvering point? That's what we're doing now. So experimental values for different CG locations and different velocities are given to you. What we need to do is plot Fs by Q for the 2 CG locations and then take their slope and plot them with respect to CG. So your CG location at which your Fs by Q, dFs by Q by dCl is 0 is your neutral point. So neutral point is dFs by Q by dCl equal to 0. That's how your neutral point, stick free neutral point is defined. Okay. So now if we are to plot this graph, so this is Fs by Q and this is CL. Okay. So if we are to plot, we take the 2 slopes. So first d Fs1 by Q by dCl. How do we do this? Take any 2 points. So I'll just take the first and the last point. Okay. So dFs by Q, this point and this point. So that is minus 0.002. Right? Are you understanding what I'm saying? Thank you. Okay, so we take the slope by the difference between the 2 points, 0.002 minus of minus 0.002 by difference between CL, that is 0.2 minus 0.4. So what is this slope? That slope is given as minus 0.02. Now similarly we do for dFs2 by Q by dCl. That is 0. Again we take the first and last point, 0.001 minus 0.001 by 0.2 minus 0.4. This comes out as minus 0.01. The slope is lesser. So the first CG you have this, and for the second you have. Okay. So I'll just plot these graphs on MATLAB and show you. 1 second. Once again, I'll just plot these graphs on MATLAB. Can you see this graph? Is the graph visible? So the blue line, like the legend says, is for XCG 0.2. That's the first value that we calculated. That is dFs1 by dQ. And this is dFs1 by dFs2 by dQ. So this is, okay, I'm not sure if you can see my cursor. The blue line is for XCG, first XCG, and the red line is for the next CG value. Okay. So you can see that the first slope is more than the second slope. The blue slope is more than the red slope. So this is the graph for dF and Fs by Q and CL. And the 2 slopes we have calculated. Okay, so now we'll go back to the screen. So what we need to do now is to plot this slope. This is 0.1, this is 0.2. You need to plot this value on another graph. So your next graph, let me just clear all the ink. Okay. So your dfs1 by q was minus 0.02 and dfs2 by q by dcl was minus 0.001. So neutral point was defined as the location where this value dfs by q by dcl is 0. Okay. So what we need to plot is the CG location at which this value is 0. So we plot dfs by q by dcl, and this is xcg. So if we take the graph here, so xcg, when the xcg was 0.2, the slope was minus 0.02. Next, your xcg was 0.25 and your slope was minus 0.01. So we join these lines, extrapolate to find this point where your dfs q by dcl is 0. So this CG value at this point gives you your neutral point. This is the neutral point, stick-free neutral point. How do we do that? We know that's a straight line. How do you find out the point of a straight line? So y2 minus y by y2 minus y1 is equal to x2 minus x by x2 minus x1. y2 is what? y2 is minus 0.02. Okay. Y is this, the coordinate at this location. This is x comma y, and in this case y is 0. Okay, so you take 0, again y2, so 0.02 minus y1 is this value, minus of minus 0.01 is equal to x2. x2 is what? 0.25. 0.25 minus x is the value that we need, by 0.25 minus 0.2. Okay, if we solve this, we get x equal to x np prime is what? If you solve this equation, how much do you get this value of x as? You get it as 0.3. Okay, we know from this graph that anyway it should be more than 0.25. So this value is 0.3. So your xnp is 0.3. Now I'll show you the MATLAB graph again for this quantity. This is the graph of the slope, that is dfs by q by dcl versus xcg. We can see here that at 0.2, your value is minus 0.02, right? Then at 0.25, your value is minus 0.01, and at 0.3, your value is 0. So where your y value, that is dfs by q by dcl, becomes 0, the x value, the CG location at that point, is your stick-free neutral point. Okay, is this graph clear? Are both the graphs clear? Yes? Are both the graphs clear? Does anyone have any doubt? Okay, I'm guessing it's clear. I'm going to move ahead. Okay, we'll go to the next question. Okay. So the next question, this is a question that sir has solved in the class, and it would help you solve your numericals, your assignment. So we'll just go over it again and just put down the equations in a systematical manner so that it will help you solve. I believe your assignment is due tomorrow. So consider the following airplane in propeller off condition being tested in a wind tunnel. The CG is 30% of the mean aerodynamic chord. The weight is given as 700 kgs. The aspect ratio of the wing is 6. Wingspan is 6 meters. Mean aerodynamic chord C bar is 1.2 of the wing. Tail aspect ratio is given. Tail span is given. A naught, that is angle of attack at 0 lift, is -2 degrees. Wing and tail setting angles are given. Lift curve slope of the wing and tail airfoils are same and they are 0.1 per degree. Tail aerodynamic chord to CG distance, that is the moment arm of the horizontal tail, is given as 6.5 meters. Elevator area is given, elevator chord, that is CE. This value is CE. Delta E naught, the intercept of that graph, delta E by CL is given as 3 degrees. Elevator effectiveness parameter, tau, is given. The downwash angle derivative is given. Tail efficiency factor and your elevator derivatives. Plus the gearing ratio, G, is given. Okay, they've also given you two graphs. So the fixed elevator graph and the free elevator. So this is the stick fixed condition, this is the stick free condition. As we've discussed before, since the stick fixed condition has a higher slope, it's more stable than the stick free elevator. Slope is the indication of stability, higher slope, higher stability. So stick fixed elevator has more slope, so it is more stable than the stick free condition. So these are the two graphs given to you. Now the first question is find the stick fixed neutral point. We will not be solving this question. I will just be giving you how to proceed with this. Sir has solved the similar questions in the lectures and it's part of your assignment. So we'll go over it in detail in the next tutorial, but we'll just go through the questions. Find the stick fixed neutral point. So at what percentage of the mean aerodynamic chord is your stick fixed neutral point? How do you find out the stick fixed neutral point? Can someone tell me? Can someone tell me? Stick fixed neutral point. Okay. So they've given you, the question has given you the CG location. You need to find out the X bar and P, right? The CG location is given to you. This DCM upon DCL, this is what? This is static margin. Right. So your static margin is given to you. The negative of the static margin is actually given to you. You can calculate this value from the graph for the stick fixed case and then calculate the X bar and P. Similarly, you can do for the stick free case by taking DCM upon DCL of the free. This is stick fixed, this is stick free. In this question, we need to use this value, the slope of this line. So it will be the higher slope. Next question is stick free neutral point. In this question, it's the same formula, but we'll be using the slope of this stick free condition, that is the lower slope. Okay, DCM upon DCL, same equation. So this value would be X bar prime and this would be X prime. Prime would be there for stick free case. Next question is wing area of the aircraft. How do you find out wing area? They've given you the aspect ratio. Aspect ratio of the wing is given here. And they've also given you the mean aerodynamic chord. Where is the mean aerodynamic chord? Yeah, here C bar is given. Aerodynamic ratio is given, center is given. You should be able to find out. Okay. Okay. Next, what is the indicated trim airspeed for stick fixed case? So they've given you density, they've given you CL at trim. Okay. What is the velocity at trim? V trim is what they've asked you to find. That is the question. How do you find that out? We've been using this equation, we've been using this variations of this equation for quite some time. So you have the lift at trim, lift equal to weight. Density is given to you. We need to find out V. We have S, we have CL. CL trim is given here. Okay. Next question. Tail volume ratio. Tail volume ratio, we just calculated in the first question of today's tutorial. Same formula. ST upon S, LT upon C bar. All these values are given to you. Okay. Value of Cm delta E in per degree. So Cm delta E is a negative quantity. We calculated this again in the first question. Now Cm delta E is given by this formula. But what is missing here is the CL alpha T. CL alpha T in this formula is for the 3-dimensional wing, not for the 2-dimensional airfoil. But the one given in the question is for airfoils. It specifies airfoil. We need to convert it into the 3-dimensional case. What the point to be noted here is your CL alpha 2D. So this value is given in per degree. CL alpha is given in per degree. So this would be 0.1 by 1 here you need to take into consideration that this quantity is valid only if your CL alpha is in per radian. So you need to do the conversion there. Conversion. Okay. Here you need to notice that whenever this term is given something like this divided by pi EAR, that means the derivative above has to be in per radians. Okay, that is what you need to remember while solving this. Next question is, if the airplane was to be trimmed at indicated airspeed of 200. So in this case, they've given you the velocity V trim. Find the tab setting angle required for CG location of 20% mean aerodynamic chord. So initially your CG was 30% of mean aerodynamic chord. Now they've made it 20%. So what you need to do, you need to calculate your dCm upon dCl has to be calculated again. Okay, it's not from the graph. Not from graph. But you've calculated your X bar NP. You have your X bar CG. You can calculate your stability, your dCm upon dCl. Okay, you have this quantity, you have this quantity. You can calculate this. So how the steps required to solve this question? First and foremost, your velocity is given in kilometer per hour, converted to meter per second. That is what I've written by convert speed. Then they've asked you to find out tab setting for trim. Trim is when Fs is 0. Okay. So setting Fs as 0, you find out this value. Fs 0. Then you find out this equation. So what is unknown in this equation? We don't know A. A is given by this. And we don't know dCm upon dCl free, which is what I mentioned earlier. We have this value. CG is the new CG location, that is 20% mean aerodynamic chord. So you can calculate this, you can calculate A. The other terms are given. Okay. Okay, here this VI would be V trim, the value that you calculated here. Then calculate DFS by DV for the CG location. Again, it's the new CG location, that is 20% of mean aerodynamic chord. Equation for DFS by DV is this. We've calculated every other value. The only missing value is K. K is given by this. All of these quantities are given in your question. You can calculate K, substitute it here. dCm upon dCl, please note that it should be the new dCm upon dCl. That is for 20% mean aerodynamic chord. That is the point that you need to remember while solving this question. With this, we end today's tutorial. Does anyone have any questions? Does anyone have any questions? Any doubts in today's tutorial or any questions? No? Are you all able to solve the assignments? Is there any doubt in today's tutorial or anything? Okay, so if not, I'm going to stop the sharing. I will share the link of the YouTube channel. You can watch these videos when you get time. Just a minute. I'm putting it up in the chat box. Okay. So if anyone has any question, please do ask. If not, we'll end today's meeting. Okay? Okay. So thank you. We'll see you again next week.